So there's one thing that I haven't managed to get to yet, and that's what I'm going to do today. And that is that Gibbs Helmholtz equation, right? Remember, that's the log of K2 over K1 being related to the delta H. And that's the K's at two different temperatures. So this is about how the equilibrium constant depends on temperature. So I'm going to go ahead and do that. And so all the excitement of the last few classes about the direction predictor equation, all of that started with this equation that we got a little while ago, and realizing that this meant realizing that you can always write this. What it meant that we could equate the volume with dGdP, and the negative of the entropy, sorry, this is a plus sign here, the negative of the entropy with dGdt. So we spent a lot of time, we used this extensively to do all that stuff with the chemical potential, and the Gibbs free energy's dependence on pressure for gases, and how it doesn't depend on pressure for solids and liquids. And this led to all that stuff with the chemical potential, and and it led to the direction predictor equation. But this equation, the partial derivative of G with respect to temperature. So this is the other part, the partial derivative of G with respect to T is equal to the negative of the entropy. And I'm telling you that where we're going with this. So the goal for this part of today is to get to this equation. And if you look at this, it's actually not obvious at all how you're going to go from this knowledge of this derivative to, figuring out this thing about how K's at two different temperatures are related to the enthalpy change. I mean, it's not obvious at all, but it's pretty clear after you do it. So, and by the way, this K2 is K at T2, and K1 is K at T1. But anyway, so what am I going to do with this thing? And why do I care about the derivative of G with respect to T at constant pressure? And that's because this tells us, of course, this is derivative of G with respect to T. So it tells us how the Gibbs free energy depends on temperature. And the reason we really care about this, we care about this a lot, and that's because we recently derived this equation, the equation you used a lot, well, used at the end of Gen Chem. Okay. Left the door open. There's a lot of stomping around going on out there. But anyway, so the dependence of G on T gives us a way into figuring out dependence of delta G, and that's delta G for a reaction, right? How that depends on temperature, and that is related to how the equilibrium constant depends on temperature. So believe it or not, this partial derivative gives us a handle on that. So it gives us a handle on how K depends on temperature. And that's something that, I talk about in general chemistry, Chem 104. So this is something that, chemists really do care about, because if we don't care about it, we don't teach it in general chemistry. So we are going to start. So to see how K depends on T, we start with how delta G0 over T depends on T, okay? Because you could see delta G0 over T is minus R log of K, and that's, you know, a very direct function of K. So to figure this out, so this is what we want to know, but we're not going to get there right away. We have to first look at, we know the derivative of G with respect to T. So what we're going to look at is the derivative of G over T, right? Because we want to get to delta G over T, but we're going to look at the derivative of G over T with respect to T. At constant pressure. All right, so how are we going to do that? Well, this is a quotient. And, you know, in calculus, you learn the quotient rule, right? And you learn that, let's see, the derivative of A over B with respect to, say, X. It's B, the bottom, times the derivative of A with respect to X plus minus A times dB dx over B squared. Okay, so we're going to use this sort of formula here in evaluating this, all right? So dG over T dt would equal, okay, so the bottom is T. That's T times the derivative of dG with respect to T, plus the top is G times the derivative of the bottom, which is T with respect to T, that's going to be 1, divided by the bottom squared, T squared. So this works out to equaling, okay, so this is T. Now the dG dt part, that's where the derivative comes in that we have from up here. That's where we're going to put negative S in for that derivative. So this is going to be T times negative S plus G times 1, right? This is just 1 over T squared. And so this is minus TS minus G over T squared. And now when you think about the definition of the Gibbs free energy, it's H minus TS. So if I just move the H to this side and the G to this side, there I have it, right? That minus TS minus G is just the negative of the enthalpy. So this is minus H over T squared. And now you could see where the H suddenly showed up. It came in. And so that's the derivative of G over T with respect to T. Now, I don't want the derivative of just, Gibbs free energy, say, of some state with respect to T, over T with respect to T. I want the derivative of the reactants and the products, and I want the difference. I want D delta G over T dt at constant pressure. And so how do I do that? Well, don't forget that the derivative of a sum is the sum of derivatives. So the derivative of a difference, well, that's just really a sum with a negative sign, right? The derivative of a difference is the difference of derivatives. So this is the derivative of a difference. So that's just going to be, and I don't want to make a big deal out of this, but this is just going to end up being minus delta H over T squared. I mean, I have some additional steps written down, but I don't think they're very instructive. Every time you differentiate, G products, you'd get H products. Then when you subtract the different derivative with G reactants, you get H reactants. So you'd end up with delta H between the products and reactants. So we have this nice formula here. And then I can take and use the fact that I had my delta G 0 is minus RT log of K. So delta G0 over T is minus R log of K. So this derivative of delta G over T becomes the derivative of minus R log of K with respect to T, okay, which is minus delta H over T squared. And then, you know, the negative R, I'm just going to move that to the other side. So I have derivative of the log of K with respect to T equals, and I'm going to have negative 1 over R times negative H over T squared. And so I'm going to end up with a positive change in enthalpy. If I do this, this is standard conditions. So I had a delta G 0 here, then it's delta H 0. So just to write it a little neater, the derivative of the log of K with respect to temperature is delta H 0 over RT squared. And actually, do you recognize this equation? Anybody here work on the chymotrypsinogen lab? Right, this was written in terms of the fraction denatured. It was like 1/4 times the derivative of the fraction denatured. But this is used in that lab. This is where we get, basically this is the formula we use, the slope of the change in the fraction denatured, which is just different from this by a small factor. So anyway, that should look familiar to you. But there's a couple of things that are done with this. It doesn't quite yet look like the formula that you used in the charge transfer lab, which was about the log of the ratio of two different Ks at two different temperatures. But anyway, let's think about this first before I go ahead and integrate it, because that this equation here that we're aiming for is actually what you get when you integrate that equation, right? This is the integrated form, but we're going to do that in a minute. First, let's take a look at this and see what we can tell. Okay, so we're interested in how does the equilibrium constant change with temperature? Well, you know, K and log K increase as K increases, the log K increases. As K decreases, the log of K decreases. So I can plot the log of K versus T, and I could look at the slope of this thing, right? Because I know that this derivative is proportional to delta H0 over RT squared. So if I think about the signs here, let's think about the signs. Okay, we know that R is always positive, right? We know that the temperature in Kelvin is always positive. But we know that delta H can be positive or negative. So it turns out that the slope of how the log of K changes with T, which is also how K would depend on T, because K and log of K they're not linear, but they're monatomic, right? One goes up, the other goes up. So we know that if the delta H is negative, this slope will be negative, okay? And if the delta H is positive, this slope will be positive. So let's first think about the positive slope. So I don't know what this graph looks like, but I'm just gonna scribble something. So this is what would happen. This is what the slope would be if the reaction is endothermic. The slope will be positive because endothermic means delta H is positive. And that means that as T increases, the log of K increases. So K increases, okay? And that means, right, we think about it this way, reactants plus heat, because this is endothermic, it's on the reactant side, goes to products. So if we increase the temperature, so we add heat, that's a stress by Le Chatelier's principle that drives the reaction to the right, increasing the amount of products and increasing the equilibrium constant. So by Le Chatelier's principle, we expect K to increase as the temperature increases for a positive delta H. Okay, and so we have, all of this stuff coming from the laws of thermodynamics tell you now that the slope is positive for log of K versus T for an endothermic reaction. So Le Chatelier's principle completely goes along with thermodynamics, right? It really comes out of thermodynamics, right? So this agrees with, I should say, thermodynamics agrees with Le Chatelier's principle. Okay, and it explains it really. And, then we have the opposite case. If you have the log of K, and instead of the slope being positive, we have the slope being negative. So then, we have a negative slope versus temperature. So now, as the temperature goes up, K, or log of K, goes down. So K goes down. And that favors the reactants at higher temperatures. I don't know if I said it here, but this favors the products at higher temperatures. Let's see. So K goes up. Yep. And this agrees, of course, with Le Chatelier's principle as well. So Le Chatelier would say we have reactants goes to products plus heat. If you add heat, you drive the reaction in reverse. So the equilibrium constant goes down. So again, we have thermodynamics and Le Chatelier agree. All right. Let's see. Yeah. So what I'd like to do, so that's something you should always keep in mind. If you have a reaction with a positive delta H, you should have a higher equilibrium constant at the higher temperature. That's like with the charge transfer reaction. You actually had the opposite thing happening, right? All the values of the absorbances decreased as the temperature went up at the higher temperature. And that meant that the reaction was not going as far to the right. So that's consistent with a value of delta H that was negative there. Yeah. I don't know about that. Did I say that right? What happened there? Anyway. Yeah. Now I feel like I have to look something up after class, but I'll do that later. All right. So I promised you I was going to integrate this. And there's two different ways to do that. You can do the definite integral and the indefinite integral. And if you do the indefinite integral, you'd have to integrate this, and you always have to make the assumption, unless you want to do a really complicated integral, in which case you'd get a separate equation for each situation. You would take this delta H0 out, the R, okay? Because, and what are you essentially doing here when you take this out is you're assuming that delta H0 is not dependent on temperature in the, okay? So you're just integrating dt over t squared, and that's equal to d log k. So the integral of derivative of log k is just log of k equals delta H0 over R, and the integral of t to the minus 2 is minus 1 over t to minus 1 t to the minus 1, or minus 1 over t plus a constant. So here is your indefinite integral. So if you plot the log of k versus 1 over t, the slope will be negative delta H0 over R. And that's a pretty good way. That's what you could do. You could get equilibrium constant at several different temperatures and do a graph like that and get delta H that way. So that's the indefinite integral. And we haven't, I don't believe we've used that in any lab. But the definite integral, we certainly have used. And so it would be the integral of d log of k equals delta H0 over RT squared. This is the same, dt. Nothing's changed there. But again, now we're going to actually integrate between two different temperatures. So this would be the log of k between, you know, at T1 to T2. So it would be log of k at T2 minus the log of k at T1, but I prefer writing it log of K2 over K1, all right? Again, you'd have to take the delta H out and the R out, of course, and so this would be delta H0 over R, the integral of dt over t squared, which is the same as what I've written on the right. Ooh, no more integral, we've evaluated it, from T1 to T2. And so this is familiar. So it's delta H0, negative delta H0 over R, 1 over T2 minus 1 over T1. So this is negative delta H0 over R, T1 minus T2 over T1, T2, which then you could get rid of this negative sign and reverse that direction. Yeah, and you have to keep in mind that this K2 is K at T2 and K1 is K at T1. And so that's how you end up with this Gibbs Helmholtz equation. It's a very nice equation because what does it let you do, right? So if you know K at two temperatures, okay, you can get the delta H0. But also, if you know 1K and the delta H, you can get the other the K at another temperature, 1K at one temperature. You can get K at another temperature. Okay. So, you know, you could solve this, you have ln K2 minus ln K1 equals, you know, you could rearrange this in different ways to solve for the different things. I'm going to go through that in an example or two later on. So that's where those equations come from. I mean, it's really straight from that crazy derivative with the negative of the entropy, which doesn't look at all like what it's going to help you with. And also this equation that we derived last time, this one here, the other important one that we use to do this. So I'm going to just now go over, I'm going to show you, I just have a handout. I think this was with something I sent earlier in the week. It was at the end of the one on the, it has that, the front of it is that has the derivation of the more general direction predictor equation. This is the last page of that handout. And so I just want to make sure you understand that, you know, when I ask you to develop the direction predictor equation, I'm asking for you to start with this equation right here. And end up with something that looks like this. Now, it's not going to look like this necessarily. This would be if you have all gas phase reactants and products. And of course, this is presuming you have the AA plus BB. You know, most of the reactions are not as complicated as this that we deal with. Okay. So you'd get an equation that looks like this, but you'd have, you know, different things in here with different powers. And that's the Q. And I also showed you that it might not always be called QP because it might have a molarity in there or something. Then we just call it Q. So I think I went over this really last time, that you start with this, and that's what I mean by develop the DPE. So what else could you be asked to do? So you could be given delta G F zeros, right? So you could find a delta G from the sum of the delta G's of the products minus the sum of the delta G F zeros of the reactants. And you need to remember that you need to multiply each of the terms by its stoichiometric coefficient. And I am going to go over some examples. Although do I do a delta G for, yeah, I think I do. So I'm not worried about that. So if you're given these delta G F zeros, and you're given the pressures of the reactants and products and everything is a gas, then you could calculate the delta G zero and calculate the Q, which you get this way. And if the answer is positive, the slope is positive, the reaction's going to go backwards. If the answer is, I better not show with my hands because it's probably the opposite. Yeah, it is. It's the opposite. And if you get a slope that's, if you get a dg dx that's negative, that's going to go, the slope is negative, which means to increase the extent of reaction would be decreasing the G. And so the reaction would go forward. So this just tells you what you would do. You'd calculate the delta G using these pressures. You'd calculate the Q, add them up, and then this is the conclusions that I just told you. Yeah. You could also use the delta G zero to calculate the log of K. And for that, you would have to solve this equation. You'd have to take the delta G zero minus delta G zero over RT, and you'd have to take E to that. E to the minus or the inverse natural log of negative delta G zero over RT would be the equilibrium constant. Similarly, if you were given the K, it might not be a KP, it might be with concentrations. And the temperature, you could find the delta G zero at that temperature. This is a little confused. Because delta G at that temperature, you just have to do the delta G zero is minus RT log of K. I think I got that a little mixed up, but yeah. So if you're solving for K from the delta G zero, you have to use this thing. And if you, I mean, it's pretty obvious if you have a K and you can get delta G using that. And this again is the repeated equation that we just derived. So it's just writing it in the two different ways. This one, this more simpler one. And if you solve for delta H, you would just have to move all of this to the other side of the equation. And that would be this. also, you can find delta G0 from the enthalpy and the change in entropy, right? Using delta G0 is delta H0 minus T delta S0. So you can be given enthalpies and entropies. And here it shows you that you can have a really interesting kind of summary kind of problem. So if you're given two Ks at two temperatures, okay, you could use the K at the first temperature to get the delta G at that temperature. Then you could use, and then you could also get use the K at T2 to get the delta G at the second temperature. Then you could use the log of K2 over K1 equation to give you the delta H. Now, this I call an estimate of the delta H because it doesn't take into account the fact that the delta H depends somewhat on temperature, okay? So this is an estimate because it assumes the delta H is independent of the temperature. It assumes that in the equation, right? The equation just assumes that we can't solve that integral until we take the delta H out. So that would give you what I call an estimate of the delta H, because it would be some kind of average delta H between these two temperatures. And then you could pick one of these temperatures, you know, so let's say T1, you know the delta G, and you can use the estimate of the delta H, and then you could solve for delta S using delta G is delta H minus T delta S, and you could solve for this. So the kinds of problems that, you know, you'll be doing on the quiz that I will give you, they're not as theoretical as some of the other problems we've done this semester. And I think that they're not as hard as some of those other ones as well. They're more straightforward. So I thought I might like to go through a couple of them with you. So let's see, 1, 2. All right, good. So here's one. Well, this one starts off with a kind of a general chemistry problem. And it says you have an initial pressure of 2 bar here. That's your initial, nothing here. And then, so you would basically have to solve kind of an ice problem, but not a very hard one. Because this would react away. So you'd lose 2x. Remember the good old x, and 3x. Is everyone with me on this? Yeah, it looks familiar. Good. So this is 2 minus 2x, x, and 3x. But I'm telling you that at equilibrium, the pressure of NH3 equals 1.956 bar. So that makes it easy to solve for this x. I think I had an extra 0 in it in the problem. And so if you solve this, you end up with x is 0.022 bar. And so that means this is going to be 0.066 bar. This is 0.022. And we already knew what the concentration of the ammonia was at equilibrium. So that's going to be the answer to this. And what is the pressure? What is Kp? Well, this is the pressure of H2 cubed times the partial pressure of N2 over the partial pressure of ammonia squared. So that's 0.066 cubed times 0.022 divided by 1.956 squared. So that's a pretty small number. Comes out to 1.65 times 10 to the negative sixth. And we'll save that for later because we need to use that for other stuff. Okay, so now the next part is develop the direction predictor equation. So, just would like to ask you, where do I start with this? Where do you always start with a develop the blah, blah, blah? You always start the same place. Anybody? dg is the sum of mu I dni. So you would write dg equals mu nh3 dn nh3, and do this for all of the three players, whether they're reactants or products. Okay. The next thing you have to do is to figure out about the dx, right? We have dx, this is the change in extent of reaction. This guy has a stoichiometric coefficient of 1, and it's a product. So that is actually the same as change in moles of N2. But for H2, we have to divide that by 3 because this is being produced for 3 for every one of these. And then this is equal to the negative 1/2 of the change in moles of NH3, because this is disappearing, and it's disappearing 2 for every N2. All right. So we always divide by the stoichiometric coefficient. You put a negative sign in front of any reactant. And so now we write the dg with that in mind. So using this, dx is minus 1/2 d n NH3. So minus 2 dx is dn NH3. So this is minus 2 dx plus mu n2 dx. That's the easy one. Plus mu H2. So now we use this guy. So 3 dx is dnH2. Okay. So we have that dg. Boy, I didn't think it was going to take up much room, did I? Didn't leave much space. dg is minus 2 mu nh3 dx plus mu n2 dx plus 3 mu h2 dx. And these dx's, they're going to go to the other side. And I'll put the positives minus the negatives. Okay, and now is where we have to make a distinction between gases and solids and liquids, but everything here is a gas. These are all gases. So the mu is mu I0. This is the standard state of the ith gas component in a mixture is the pure gas. And then we have RT times the partial pressure. So this will be 3 mu H20 plus RT log of the pressure of H2 plus, for nitrogen, mu 0 minus the mu zero for ammonia plus RT log of the partial pressure of ammonia. And all of these zero ones, standard ones, they move over, they'll be taken out. So we have 3 mu 0 H2 plus mu 0 N2 minus 2 mu 0 NH3. Okay, plus everything else, RT. So we'll have 3 RT log of pressure of H2 plus the log of the pressure of N2 minus 2 times the log of the pressure of NH3.
Dr. Cooley, does the RT in the first term, it comes out, right?
Oh yeah, this is gone. Yeah, I factored it out. So these are just, you know, what was the reaction? The reaction was 2 ammonia going to 3 H2 plus N2, all gas. So taking 3 times the standard molar Gibbs free energy of hydrogen and 1 times the standard molar Gibbs free energy of N2 minus 2 times the standard molar Gibbs free energy of NH3, that's just the delta G0 of the reaction. And this is going to be RT, and this 3, now I'm going to put it over here. Okay, and this -2, okay, so the 2 will be now a squared. So this will be RT, the log of PH2 cubed times PN2 over, because it's negative, PNH3 squared. That's our direction predictor equation for this particular situation. Okay. All right. All right, so it asks, what is delta G0 for this reaction? How am I going to figure that out? Because I haven't given you any information on delta G0s, but we have calculated this equilibrium constant. So that's what we're going to use here. We're going to use that delta G0 is minus RT times the log of K, which we got from the equilibrium pressures of all of those gases. So this is, let's see. So just to be sure, you know, this is 8.314. We'd have to use, I would use this in kilojoules per mole Kelvin, 298 Kelvin. I don't think anything, I don't know if I even mentioned the temperature in this problem. I did as 298, but if I didn't, you'd assume it was 298 unless told otherwise, times the log of the K. And so this comes out to 33.0 positive. Let's see, does a sign work out? This is minus, I forgot the negative sign here, but this is negative. This log is less than 1. So you end up with a positive 33 kilojoules per mole as your delta G0. It really only has 2 sig figs actually, because this really only had 2 sig figs. Okay, whatever. So then a lot of times you're asked to make a rough sketch. So I mean it really, it doesn't have to be anything but rough. So that means you're going to plot the Gibbs free energy versus the extent of reaction. So what do you know here? You know that you have a positive delta G0. So that means that this difference here, that this is going up, right? This is a positive delta G0. You end up with a higher delta G0 than what you started with. And what is this? okay? This, I would say, is the sum of the standard Gibbs free energies of the reactants. And I wouldn't, you don't have to write down what they are, just write that. You know, really what they are, you can go back here, you can see it's actually, this is what the reactant one is, and this is what the product one is. But there's no reason you'd have to put that in. This is just a sketch. But the thing you do have to be careful about is where are you going to put the minimum? So where will the minimum be? Sorry, did you say? It's going to be on, what did you say? The left. Yeah, I think you said the left, right? That's going to look something like this. Okay, the minimum has to be on the left because the minimum is always on the side of the lower Gibbs free energy. And if that's the reactants, then the minimum is going to be on the left. So this is your equilibrium here. What else? That's about it. So equilibrium is on the reactant side. Because delta G0 is positive. Okay. So which direction will the reaction, wait a minute, did I skip a problem here? Okay, yeah. So now it says, which direction will the reaction go if the partial pressures are PN2 is 0.010 bar, pH2 is 0.030, and PNH3 is 20. So let's just look at this. Here's the reaction up here. So what this is a very large concentration of the reactants, right? This is 20 bar and it hasn't gone forward very much. So, so where are we? You know, what is, so in order to actually answer this question, you have to calculate dG dx under these conditions, right? So it's going to be delta G0, which we already know, plus RT times the log of Q. And Q is the pressure ratio. And we know this is not at equilibrium, but we still have to use that pressure ratio. So this is going to be, if you look at the reaction, it's going to be pressure of N2, pressure of H2 cubed over the pressure of NH3 squared. So what's given, let's see, N2 is 0.010. Let me write it down here. 0.010 times 0.030 cubed over 20 squared. Okay. And I actually didn't calculate that, but I should calculate that. It's actually 6.8 times 10 to the negative 10th. So it's a pretty pretty small number. So this is 33.0, that's the delta G0, plus 8.314 times 10 to the negative 3 times 298 times the log of 6.75 times 10 to the negative 10th. And it comes out. So this term, it's actually 33, is negative, right? This is negative. And then we have a positive here. So this is negative 52.32, which is negative 19.3. But the big deal here is that it's negative. Okay. So if we take a look at our drawing, where is this on the drawing? So this is a relatively pretty These are large concentrations of reactants, and the slope here of dg of G versus X is negative. This is a negative slope here, so it has to be somewhere over here. All right, it's going to be somewhere over here. So basically, we're at the beginning of the reaction that most of the concentrations from here to here, the reaction would be going to the left, but we are still at a very low concentration, okay? So due to the low concentrations of the products, the reaction is still going forward. It hasn't gotten to equilibrium yet. So actually, we'll write that down. These low concentrations or pressures of the reactants, the reaction has not yet reached equilibrium. So it's still going forward, right? So despite the fact that the delta G0 is positive, which in freshman chemistry, you would say, oh, this reaction is going to go in reverse. But that's only under standard conditions. These are not standard conditions. Okay. So which brings me to the next question, which is which direction will the reaction go if everything is at a standard pressure? So if all the pressures are 1 bar, then the dg dx is delta G0 plus RT log of 1, which is 0. So everything is determined by the sign of that delta G0. And delta G0 is positive. So dg dx is positive. So that's a positive slope of G versus X. And so that will go backwards. It will go in reverse. So that would be somewhere over here on the diagram. Somewhere over there. We know it's somewhere. We don't know exactly where. Okay. All right. Are you following all this okay? Okay. So I don't know. So then I tell you what the pressure, what the equilibrium constant Kp is at a higher temperature, 700 Kelvin. Look at the difference here. So you should be able to tell right away what the sign of delta H is. Okay, remember we had an equilibrium constant that was like 10 to the minus 6 at 298, and now it's exploded and it's 3,000. So the K increases with temperature. So that means delta H0 is going to be positive. So I told you this before in lab, but I'll tell it to you again. When you go to use this equation, I wanted to do something else first. Well, I might as well do this. So what I'm doing now is answering this question, find the delta H. What I wanted to show you was we do it on the side here, the delta G0. We'll do that later because we can also get the delta G at this new K as well. But anyway, let's do the sign. Let's do the delta H. So what I've told you in the past with my method, my trick that I always use is I always make T2 the higher temperature, right? And I use this formula, the log of K2 over K1 equals delta H0 over R, T2 minus T1 over T1, T2. Now, if you look at this version of the equation, if T2 is greater than T1, which I always make it, then this is going to be positive. Okay. And if delta H is positive, then K2 should be greater than K1, right? This ratio here, if K2 is greater than K1, the log of that ratio is positive. And that will give you a delta H that's positive, because this term here is always positive. So I just keep that in mind all the time in case I'm going to make a mistake. You know, I don't want to make a mistake and get it wrong. But so how would you solve for the delta H? Well, you just have to move this and the R over to the other side. So I'll just make it T1, T2 over T2 minus T1 log of K2 over K1 with an R somewhere equals the delta H0. Okay. So, you know, just put in 298, 700 over 700 minus 298 times 8.314. You can put it times 10 to the negative 3, or you could divide by 1,000 later if you want. Log of 3170 over 1.65 times 10 to the negative 6. This is going to be a positive number with a much bigger number on top. And putting all that in, it comes out to 92.2 kilojoules per mole as the delta H0. Okay. So now it says, is this a reliable value? So what can you say about this value? You know, what's assumed about it in order to figure out what it is? We have made a pretty egregious assumption, actually, because this is a temperature range from 300 to 700 Kelvin. So we're basically saying over a 400 degree temperature range that delta H doesn't change at all. Because remember how this equation was derived. It was derived by assuming that that the delta H was constant over that temperature range. So it's basically an estimate because it's assumed that delta H is constant between 300 and 700 Kelvin. And maybe it doesn't change by that much. We've done calculations, but I don't think ours were over a 400 degree temperature range. So that's the answer to this question. Does the sign of the value agree with what you'd expect from Le Chatelier's principle? So we had K2 is much greater than K1, right? 3170, 1.65 times 10 to the negative 6. So that means if we had an endothermic reaction and we add more heat by increasing the temperature, it's going to drive the reaction to the right, increasing the K. So K2 will be greater than K1. So that works because K2 is greater than K1. So it's consistent with Le Chatelier's principle. I did want to show you something else that wasn't asked in this problem, but I want to point out something to you. And that is, if you take the K at the higher temperature, this is at 700 Kelvin, you can use it to calculate a delta G at that temperature. And it's going to be a lot different from the delta G at 298. Well, we know that because the K is hugely different, and delta G0 is minus RT log of K. So, you know, these delta G0s are not constant with temperature. They're just not. And that, you know, makes it more interesting, right? So here at 700 Kelvin, the delta G0 being minus RT log of K would be minus 8.314 times 10 to the minus 3. Now you would have to put that 700 in there, okay, because that is the temperature we're talking about, times the log of 3170. Okay, now when you put that in there, now, of course, this is a positive number now. So you're going to get a negative delta G0. Let's call it negative 47. And, well, let's just leave it because I need the room. And if you're going to draw your diagram now it's completely changed, right? Before we had a positive delta H, delta G 0. Now we have a negative 1. So we're going to have an equilibrium on the product side. So this is what it looks like at 700 Kelvin. And this is what it looks like at 298 Kelvin. It's very, very different. Yeah. Anyway, so that's what can happen with reactions. So there's a lot of stuff that you can get out of a small amount of data. Well, probably a lot of data, but it's just like K's at 2 different temperatures. You can also get a delta S for this reaction because you know that delta G is delta H minus T delta S. So if you solve it, delta G0 minus delta H0 over minus T is delta S0. So you can just flip it around, get rid of the negative sign, and you get this equation. But of course, this is based on the delta H, which don't forget, that is an estimate. So this becomes an estimate as well. All right. And in this case, we have 92.2 minus 33. That's your delta H minus your delta G over 298, because I use this at 298. I could get an estimate of delta S at the higher temperature by using the 46.9 here. But this is at 298. Okay, so this is at 298. So that comes out to 190, well, it comes out to 0.199 kilojoules per Kelvin per mole. But we usually express entropies as joules per Kelvin per mole, and it's positive. Okay, so if you think back to this reaction, notice you have 4 moles of gas and 2 moles of gas. So it makes perfect sense that this should be positive because there was an increase in moles of gas. All right. What else? I think that's really all for this problem. That's long enough, right? That was a pretty long problem. Okay. So do you want to do the next one, or do you want me to skip it and just call it a day? Let's do the next one. All right. Somehow I think I'm going to need more room for this one as well. Oh, come on. All right, so on to the next one. So here we have 2 of the same gases, but forming ammonium chloride, which is a solid. So when we develop the direction predictor equation, we're going to have to remember that mu is equal to mu0 for the NH4Cl. We're not going to have an RT log of P term. So we start with dG is equal to the sum over I of mu I dNi. So that's all 3, mu NH3 dN NH3 plus mu HCl dN HCl plus mu NH4Cl, Dn NH4Cl. And here we have a very nice extent of reaction because there's all coefficients of 1. So dx is the change in the moles of the ammonium chloride, or the negative of the change in moles of NH3, or minus DnHCl. Yeah. So that means when I take this and go to the next step, mu NH3 times minus dn, minus dx, I should say. Right, I didn't take that, but you know, dx is minus dn NH3, so minus dx is dn NH4Cl. Oh, duh. Why did I put NH3? That doesn't matter. It doesn't matter the order. Plus mu HCl dn. Yeah, minus dx plus mu NH4Cl dx. Okay. So negative signs in front of all the reactants, positive sign for the product, and there are no coefficients, so we're good. So then dg dx is just this, mu NH3 plus mu HCl plus mu ammonium chloride. And then these two, you just add the RT log of the pressure to the standard Gibbs free energy for NH3. I forgot to write that in. And here we just have, we don't have any, this is a solid. Solids or liquids, mu equals mu 0. There's nothing else that's needed. So grouping the mu 0 terms, I feel like I'm getting this backwards. I am getting it. What's going on here? Yeah.
What happens to the negative?
Negative. Sorry?
I was just asking what happened to the negative sign.
Yeah, I lost the negative. There we go. So this is RT times the log of, okay, so there's a negatives in front of those, and there's nothing here. So we basically have 1 over PNH3, PHCl. So this is going to be the Q. It's just dividing by those partial pressures of the two reactants. So this is mu 0 of the product ammonium chloride minus mu 0 of each of the two reactants plus RT log of 1 over PNH3 PHCl. Okay. This again, that is delta G0 for the reaction. And so this is the DPE. This is the QP. All right, so now the question is, find the equilibrium constant, find Kp. Well, I mean, we're not given the Kp, but we're given delta G F0. So we're going to use the delta G F0s to calculate the delta G0 for the reaction. And then we're going to use delta G0 is minus RT log of K. So minus delta G0 over RT, e to that is the K, or the Kp. That's how we're going to do this. So I think we're going to need a little more space here. Okay, so delta G0. All right, let's get that. That reaction is NH3 plus HCl gas goes to NH4Cl. So we have G F0 of the ammonium chloride, solid, minus delta G F0 of HCl, minus delta G F0 of NH3. Okay, so that's negative 202.87 minus negative 95.3. I always distribute my negative sign first. I don't wait to do it because I'll forget. So this is minus 91.12. That's the delta G0. So I would go e to the minus 91.12 over 8.314 times 10 to the minus 3 times 298. Come on, what's going on here? It just wants me to write the same thing 3 times. This is some gigantic number. Oh. Wait a minute, hold on. E to the minus delta G, so it's negative of this. Oh shoot, the answers are wrong. I don't have that negative in there, but anyway, it's just huge. It's 9.39 times 10 to the 15th. So huge. So basically, this is like going to completion, basically. Yeah, hold on a minute. So this drawing here, where is it? Does it ask me to sketch it? Yeah. So it's hard to sketch it when it's so far to the right, right? It's so overwhelmingly far to the right. It's kind of like that, you know, the equilibrium. This is even exaggerating its distance from the x equals 1. But oh well, that's what we got here. It doesn't matter. Like I said, these drawings don't have to be beautiful. So it's very, very big. So the products are heavily favored. The reaction basically goes to completion. Yeah, I mean, we'll talk about what that means. So in freshman chem, we would say, oh, this reaction goes to completion. But now we're actually going to be able to calculate, you know, well, I'm going to be able to show you that for a certain pressure, the reaction will actually go the other way. But it's a very, 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 very small pressure of the two gases. Okay, so it's almost all the way to the end here that, you see there is a little bit of space for the reaction to go back. But in reality, that's really a tiny, tiny bit. But anyway, so which way will the reaction go under standard conditions? dg dx is just equal to delta G0, which is negative. So it goes forward. So the standard conditions are somewhere here. I don't know where exactly, and I don't care. And this is mu reactants sum, and this is mu zero products sum. Okay. So that was part C. And now, if PHCl, if these pressures are all 0.02, which way will the reaction go? So those are pretty low pressures of these reactants. So you'd think you'd be pretty far over to the products. Maybe it would go back the other way. But in fact, that's not true, because QP was 1 over PHCl PNH3. So we have to calculate delta G0 plus RT log of that QP. And this is 1 over 0.020 squared. Which is 2,500. So the delta G0 was minus 91.12 times RT is 298 log of 2,500, which is positive. So this is plus 19.38. So we're probably over here somewhere, we're further to the right. We have smaller concentrations of reactants, which means we're closer to products, but this number is still very negative. So it's still going forward, even at these pretty low concentrations of ammonia and HCl, okay? So this one now, look at that concentration. That's 10 to the minus 9th bar. I don't even know. There are probably labs that could measure that, but yeah, I'm sure there are, but it's not that easy to do. So what happens if those pressures are that low? Okay, so now when you put that number in there, this dg dx, I forgot to write that here, is the delta G0 plus RT times the log of 1 over 1 times 10 to the minus 9th squared. So obviously, this is going to be much different. This is still minus 91.12, but now we add 102.7 to that. That's positive. And it comes out to a positive number. So at these really incredibly, I didn't do it. At these really low concentrations of ammonia and hydrochloric acid gases, the reaction does go in reverse because this is positive, slope is positive. Okay, so we are finally over into this part of the graph. It's terrible drawing, but it's over here. Okay, so this is from part, what part was that? Part E. This is part E. Okay, so it's going backwards because it's at that very end there. When you have almost no reactants, yes, it will go backwards. So obviously the products are heavily favored in this reaction because of the large negative delta G0. Okay. And also you can estimate the K at 500 Kelvin. Why is it an estimate? I've told you that before. So here we're going to use that equation a little bit differently. And that's because you're actually given the delta H F0. So you can calculate the delta H0. Okay, so it would be, let's see, the delta HF0 for the ammonium chloride minus times 1 minus delta HF0 for the ammonia minus the delta HF0 for the HCl is the delta H. So you could put those numbers in. Minus 314.43 for the ammonium chloride, minus 46.11, that's the ammonia, minus 92.31 for the HCl, and it comes out to negative 176.02. So it's very negative. So the log of K2 is the log. Now we know the K, that huge K that we calculated earlier, plus now we know this is negative 176.02 divided by R times 500 minus 298 over 500 times 298. Yeah, and you should probably be careful, right? But you know that the delta H is negative. So for sure, the K at the higher temperature is going to be lower. And it is. It comes out to this, well, the log of K2 comes out to 8.09. So K2 is e to the 8.09, which is still a big number. So it's still big, but it's not as big. Okay. As it should be with a negative delta H. And then one more thing, you can calculate the delta S. You should realize that the delta S is negative because you're losing moles of gas. But you can use that formula. You can rearrange the delta H. Delta G is the delta H minus the T delta S formula to solve for delta S0. Oh, it doesn't actually ask you to do that, so you're not asked to do that. But you could do that. And you would use this method. But it does ask you to, as 2A, I don't even have H here. It says to discuss the spontaneity. of this reaction. And so what I would do there is I'd say, okay, let's look at the signs of these things. Okay, let's see. We'll see that the delta H is negative. The delta S is negative because we've just figured this out. So this term is positive. So what does that tell you about the spontaneity and its dependence on temperature? So when the temperature is low, the delta H term dominates. And the reaction is spontaneous because the delta H is negative. But as the temperature goes up, the magnitude of the T delta S term grows and becomes more important. So eventually, the negative T delta S term is going to win. Entropy always wins as the temperature goes up. And the reaction becomes non-spontaneous. We haven't seen that yet at some high temperature, but not at the temperature we use. What was the temperature? Not at 500, maybe at 700 or something like that, but not yet at 500, but it does have a lower K at 500. And it would have a less negative delta G0. Delta G0 minus RT log of K. We could calculate that. And that comes out to a negative 33. Right, it was like negative 91. Okay, so it went, this is what it's like, right? At 298. Now it's not quite so, right? The equilibrium would be, wouldn't be as far. And you could see that as this difference changes, it's going to move, it's going to become, it'll go the other way eventually. So that temperature plays a big role, T delta S, the T delta S part of delta G. It's kind of a big deal. Anyway, that's all I really have to say. I think that's more than enough. Time is it? Oh my God, it's late. Anyway, yeah, get those lab reports in, please.